All right, so here we're going to check out section 2.3. To be perfectly honest with you, there is absolutely nothing new in this section. However, I think it's probably the best section because it really does bring everything together. And this is kind of the culmination of everything we've been talking about, big picture wise. This is when it all comes together. Okay. So we've been talking about a lot of this stuff here, but there's this ultimate thing that kind of ties it all together. This is what's known as the invertible matrix theorem. Okay. So if A is a square n by n matrix, the following statements are logically equivalent, meaning they're all saying basically the same thing. If one's true, they're all true. If one's false, they're all false, right? They're all saying basically the same thing. Now, we'll get to this in a minute. But keep in mind, we are talking about a square matrix. It turns out if A is invertible, in other words, A inverse exists, then the transpose is invertible. There has to be a matrix that, some other matrix you can multiply on the left to get the identity. There also has to be a matrix that you can multiply on the right to get the identity. You actually even know more than that, but that'll make more sense if we check out some examples. Okay. But basically, it's the inverse, right? But it would actually be on both sides. We'll see that. Okay. A is row equivalent to the n by n identity matrix. In other words, you can take A and you can row reduce it to the identity, right? You use all the correct row operations and it'll basically reduce down to the identity. Okay. It has n pivots positions, meaning every column is a pivot column. Okay. The equation AX equals 0 has only the trivial solution. The columns of A form a linearly independent set. None of the columns are linear combinations of each other, basically. The equation AX equals B has one solution for every one, right? That basically implies the columns of A span, right? All saying the same thing, right? All these things are all saying the same thing, basically, if you have an invertible matrix or any of these. The last two things here we didn't talk too much about, but they're just terminology for the same thing, right? So we did talk about a linear transformation, but transforming X into AX, in other words, it's a transformation, right? It was input, output, right? It's a function kind of thing. If I input X and you multiply by this matrix A that they're talking about, then that maps Rn onto Rn. Basically, R onto, that phrase onto is the exact same thing as span. Think of onto as it covers all of it, right? So it literally goes onto it, right? So think of it as if you're talking about if your inputs here are Rn, then your outputs over here are Rn, and it literally is going to cover the whole thing, right? It's different terminology, but it's the exact same span, meaning it covers the whole thing. One to one is literally the same thing as this, right? Just like with functions, you stick one thing in, you get one thing out, right? Also works the other way. Each thing out came from only one in, but basically that's saying that everybody's got a solution. Okay, different terminology for basically saying the same thing. Okay, so I think what I'm going to do here is there's nothing new at all. But I think we're going to check out a couple of different examples with some different matrices just to explore how this idea works. Okay. And definitely kind of go through all the different pieces and parts to it. Okay. So it's kind of a good culmination of how all these different ideas. All right. So let's say this first one. I got this matrix A here 1, -4, -3, 13. Okay. So we just rewrote it over here. So what I want to do is basically go through all these different things and show you how this works. Okay. So for that first example, so first off, we do indeed have a square matrix. Okay, so a square matrix, that means I'm okay, right? So, this is a square matrix, so it's possible these could all be true. Okay. First of all, the question I want to know here is A invertible? Or in other words, can I find the inverse? Okay. You can check it out before. We did that in the previous section there's a formula for it. But if you remember the quick way is to look at the determinant, right? You can determine if it's invertible or not. So remember the determinant, like it's kind of cross multiplying. So it's like 1 times 13. Oh my God. 1 times 13 minus then here the -4 times -3. Or basically you were looking at 13. This is going to be a positive 12. So minus 12, which is 1. Now here's the point. This is not 0, right? So if the determinant is not 0, then what does that mean? You've got yourself an invertible matrix. This means that A inverse exists. Okay. So if A inverse exists, that means everything else here has to be true. Okay. So There's a formula for it, but basically we can actually find it then, right? So A inverse, if you remember, was 1 over the determinant, which in this case was 1. And then if you remember, you flip these. So this would be 13, and this would be 1. And these, you switch the sign. So this would be 3, and this would be 4, right? So there is your inverse. And you could check it out just to prove it. Mhm. Oh, I think I already have that on there, but whatever. 1, -4, -3, 30. No, what am I doing? 2 by 2, right? 1, -4, -3, and 13. Okay. Then let's put the inverse in for B here, right? So what did we say that was? 13, 4, 3, 1. Okay. So the whole point here is, remember what the whole point of an inverse is if I took that matrix A and multiplied by what we're thinking the inverse is, which was I stored it into B, if I did A times B, sure enough, you get the identity, right? That's how you check that you really do have that inverse, right? So it is indeed true that A times A inverse is the identity. Also, you probably should at least check it. But then what does that mean? That means if I were to take B and multiply by A in the other order, or the inverse times the original function, you still get the identity, right? But either way, right? So that's truly its inverse thing, okay? Then to just kind of go through, I mean, the second one here is kind of silly, but it is true that the A transpose would be invertible as well. So it's worth at least talking about that. So first of all, what would A transpose be here? Well, remember the transpose, remember the rows and the column switch. So instead of being 1 -3 this way, it'd be 1 -3 this way. Instead of -4 13, it would be -4 13, right? But the point is, this would also be invertible, okay? You can figure that out by looking at the determinant of the A transpose. But what's the determinant here would be 13 minus 12, which is 1. If you step back and think about that, that's always going to be the case, right? If you're talking about a 2 by 2 matrix, when you go to find the transpose, what is the determinant of the transpose going to be? The same thing, right? Because basically, when you multiply these, that's going to be the same. When you multiply these, yes, they have flipped, but when you multiply them, you're still going to get the same thing, right? So it's going to be the same determinant. Okay. It's worth talking about, but what would A transpose's inverse be? Okay. Well, again, it's 1 over the determinant. And then remember, you flip these. So this would be 13 and this would be 1. And then these you would change signs. So now this would be 3 and this would be 4. Okay. But it is worth looking at. Oh, look, there it's the same inverse that we had here. But, instead of 13, 14, it's 13, 14. Instead of 3, 1, it's 3, 1. Or this indeed is actually the inverse's transpose, right? Either way, it works, right? So whether you're talking about the inverse of the transpose or the transpose of the inverse, you still get the same thing, okay? But ultimately, the point there is if A is invertible, the transpose is invertible. Okay, great. 3 and 4 are kind of silly, if you ask me, but they'll make more sense later when we look at a different example, right? So it's worth mentioning, but 3 and 4, we can do this together. Is it true that there's an m by n matrix here? Well, yeah, but it's the inverse, duh, right? So I mean, we just saw it, right? I mean, like it's literally on the left. You can start with this A, and on the left, I can find a C that'll get me to here. It's called the inverse, right? And technically, it is the same thing here on for number 4 there, right? Can you multiply by something on the right to get to the identity? Yes, it's called the inverse. Okay. The reason why I want to stress this is because we'll get to a different example in a minute, but it's possible to take a matrix and multiply by something and end up with the identity, even though it's not invertible, right? That's why there's a stressful here. So we got to make sure that we're getting to the point here of is it possible to, in general, I'm not talking about a square matrix, I'm not talking about this A here, but in general, is it possible to take a matrix and multiply by something on the left and get to the identity and it not be invertible? Yes, it is. Is it possible to take a matrix and multiply on the right by something and get the identity and have it not be invertible? Yes, it is. Okay. If it's a square matrix and this happens, then it has to be invertible. That's the key, right? That'll make more sense to some other ones. But if you got a square matrix and you can multiply on the left or the right and you end up with the identity, duh, it's invertible. Okay. All right. What about 5? If I were to look at 1, -4, -3, 13, right? Just so we're not here all day with this stuff, use a calculator. I mean, you can do it by hand if you like. But the point there is, if I take that matrix, remember A, I already got it stored in there, right? If I were to take that and row reduce it, in other words, reduced row echelon form of that A, sure enough, it gets to the identity. Okay. So indeed, this does row reduce without showing all that work to the identity, right? That arrow meaning row reduces to the identity. Okay. So if you got an invertible matrix, if the inverse exists, it has to be row reduces. Okay. But 6, does it have n pivot position? Is every column a pivot? Yes, it is, right? That's the whole point, right? With 6 here, you can see all of these. These are all pivot columns, right? Okay. What about 7? The equation Ax equals 0 has only the trivial. Well, of course. I mean, like, if I wanted to take this equation and solve it, how would you do that? You would take A and augment it with the 0, right? So you could go the long way and you could set it up. So this is 1, -4, -3, 13, right? And then you could augment with the 0 matrix without doing any work. We already know if I row reduce this, this is going to turn into the identity. And no matter what row operations I use, these are all zeros. This is never going to change. So what does that mean? You indeed have a unique solution 0, right? So if another way you could see that also is, instead of row reducing it, remember the inverse exists. So I could take this equation here and multiply by the inverse because the inverse exists. So here, this is going to turn into the identity times x, but that's just x. And then over here, what's this matrix times 0? If you multiply everybody by 0, you're going to get 0, right? So whether you see it from the matrix algebra stuff using the inverse idea or row reducing it, either way, only solution is going to ever be 0. Okay. The columns of A form a linearly independent set. Well, duh, right? So the point here is, if I think of this set A1, A2, right? So really it's this collection of vectors, namely the vector 1, -3, and what was it, -4, 13, right? This set or collection of these two vectors, do they form a linearly independent set? Think of it as they're both pivot columns, meaning, right, they are not relying on each other. There's no dependency between them. There's no dependency, right? They're, it basically follows from they're both pivot columns. So if they're both pivot columns, or there is no dependency, right, then of course it forms a linearly independent set. Okay. Then 9, none of the columns of A are linear combinations of each other. Well, duh, right? I mean, that literally follows directly from that. That's literally the same thing. But another thing to mention here is there's only 2 of them, right? So if there's only 2 of them, the only way these could be linear combinations of each other is if they were scalar multiples of each other, right? Or in other words, think of it as, is it possible I could take some number and multiply by that first column and end up with the second one? No, right? Because look, if I multiply the top one by -4, that is certainly not going to turn the bottom one into 13, right? There's no scalar you can multiply this whole thing by and get to here, right? So no scalar exists. So if no scalar exists, you clearly they're not scalar multiples of each other, so they are not linear combinations of each other, right? All right, what about 10? If you were to take this AX equals B, right? Would this have at least one solution for every single B? Sure. I mean, like, the whole point there is, one way you could do that is you could take A and augment it with B, no matter what B is, any B you want of the appropriate size, right? You could take it and do 1, 0. No, what am I doing? That's the answer. Oh, no, it's 1, -4, -3, 13, right? And imagine, there's a B1 here, B2 here, right? Whatever this vector B is, no matter what it is, I can set it up. But the point is, without doing a whole lot of work, you're going to see it's 1, 0, 0, 1, right? Then clearly this is going to change, this is going to change. But the point is you're going to get a answer, right? You're never going to get a no solution. You're never going to get a row of zeros here and a number here, right? I mean, clearly the B1 and the B2 are going to change, but, it would still work, okay? Or you could think of it as no matter what my B is, instead of row reducing it, I could use that inverse idea again. So what is my solution going to be? It's literally going to be the A inverse times whatever B is, right? So by row reducing it or using this inverse idea, you will always get one unique solution every time, okay? But then the whole point there, without doing a whole lot of work, if you always get a solution, no matter what the B is, then that literally is the definition of span, right? Because it spans all of Rn. No matter what I do, no matter what vector I pick here, I can always get an answer. That's what span means. It means spanning all of Rn, covers the whole thing. Without a whole lot of explanation, they're onto literally the same thing, right? I wouldn't worry too much about this, but it's true. Onto meaning that if I think it was a transformation, everything is everybody's got a buddy, put it that way, right? That's what onto means. It maps onto on the whole thing. One to one is basically the same thing as saying there's always one, right? So if I pick anybody in here, you can always get one out. Or everyone out came from everyone in, right? It's literally saying the same thing. Okay. All right, let's check out a different thing. Just to make the point. So let's look at B. Okay. So with B, you've got this 1, -2, -3, 6. All right. The first thing is it a square matrix? Yes, it is a square matrix. It's clearly a 2 by 2. So if it's a square matrix, then all of this is possibly true, okay? Or it's possibly all false. Okay. So now the question is A invertible? Well, or that B, whatever. So with that first one, we can look at the determinant of B. So the determinant of B would be 6 minus, whoops, 6, which is 0, right? You see that 6 and then minus and then multiply here is 6. So determinant is 0. So then what does that mean? That means B inverse does not exist. Or in other words, B is, remember, what's called singular. He doesn't have a buddy. He's all by himself. He's single, right? So then what does that basically mean? Everything is false, okay? So if B doesn't have an inverse, then B transpose 1, -3, -2, 6 also, right? 6, same thing, -6, doesn't have an inverse, okay? So what that means, like with 3, is it possible to multiply by something on the left and get the identity? So is it possible to multiply by something and get the identity? The same with 4. Is it possible to multiply by something on the right? Well, they called it D. To get to I, right? No. So no C, no D exists, right? So it's not, since it's a square, the only way this would work is if this were the inverse, but it doesn't exist. It doesn't exist. So no such thing exists. Okay. What about 5? Row equivalent. Is it row equivalent to the identity? So if I were to take this 1, -2, -3, 6, and I don't know, maybe if you stare at that long enough, you might be able to row reduce that without doing any work at all. Maybe you can, maybe you can not. Maybe not yet. You'll see in a minute. But let's say okay, so there's my matrix: 1, -2, -3, 6. Okay, and if you do it by hand, whatever. But if you take, oh no, I want to row reduce. If you take that matrix. Did I? Crap. No, what did I put in? Did I put it in A? Yeah, I did. Okay, so 1, -2, -3, 6. All right, so I want to row reduce A, but look what you get. You don't get the identity. That's the point. Okay. So you are going to get 1, -2, 0, 0. Okay. Which is not the identity. Okay. So since this particular matrix is not invertible, it's not going to row reduce to the identity. Okay. Then the same with 6, right? So here, are they all pivot columns? No, not all pivot columns, right? Then what does that mean about 7? The equation ax equals 0, does it have only the trivial solution? So if I were to imagine bx equals 0, right? Are you going to get only the trivial here? No, you are not, right? Because if I took b and set it up augmented with the 0, right, without writing it all, what is b going to row reduce to? It's going to row reduce to 1, -2, 0, 0, and that 0 is never going to change, right? We now have an infinitely many solutions, right? So with this, again, basically what this is saying is that there's a dependency here, right? So x1 would be the same as 2x2, right? This is your pivot, this is your non-pivot. So the x2 is free, and x1 would equal 2 of those x2s. Or in the general vector format, basically you can think of it as x2 is whatever it is, it would need itself, but x1 would need 2 of them, right? Or basically what this is saying is any solution to this homogeneous equation is a scalar multiple of this vector 2, 1. Okay. And I don't know, maybe it's just me. Duh. Stare at that for a second, right? Look at the first column and look at the second one, right? If you double this, it's the opposite. If you double this, it's the opposite. Clearly, if you have 2 of these, that first column, and 1 of these, you're going to get 0, right? 2 of these minus 2, 2 of these 6, you're going to get 0, right? But that's the point. The homogeneous solution that you see right here literally gives you your dependency. So do the columns of A form a linearly independent set? No. So basically 8 and 9 you can do together, right? If you just stare at that long enough, you can see 2 of that first, no, I call them B, whatever, but 2 of that first column would clearly give you B2, right? 2 of these, well, actually, they'd be the opposite of each other, sorry. So -2 of these would give you these, okay? But there's your dependency, okay? Or in other words, we have a non-trivial solution to this homogeneous vector equation, okay? So there is clearly a dependency happening here. But that's the point. I mean, especially when there's only 2 of them. I mean, if you just stare at this, you can do it quickly. Because if you just look at them and say, look, okay, if these are scalar multiples of each other, then you do indeed have a linear combination of one as the other one. They're scalar multiples. So I guess when you got a nice 2x2, that's your best friend, right? That's the one that's easy to see, right? If you only have 2 of like a 2x2 and you can see that they're scalar multiples of each other right there, then everything else is false. That's the point. Okay. So then what does that mean here, right? So the columns with the equation, is it going to have at least one solution? No way, right? That means there's going to be some things I can't get to. That would lead into what is the column or the well, col is what it's called, but it is the column space. We don't know what that is yet. You'll see. But does it span all of Rn? No way, right? Because there's certain things we can't get to. It's probably worth doing that. So what am I talking about? So with 10, we're looking at, well, I called it B. Keep doing that. What was this? 1, -2, -3, 6. Okay. Now I can't use matrix algebra here. I can't use B inverse to solve this for X because B inverse does not exist. So the only way to solve this, since I can't use inverse, is you would have to set up an augmented matrix, with that generic B1, B2. And you could row reduce this if you wanted to, right? Just to show you, right? So this would be 1, -2, B1. And then here you can multiply this by 380 to get the 0 here. So 3, -6, 3B1, right? So this would be 0 here, 0 here, and then this would be 3B1 plus B2. All right. So now what does that mean? That means if 3b1 plus b2 equals 0, right? If this number equals 0, that means you have a solution, right? If 3b1 plus b2 is not 0, then you can't get there. X does not exist. So basically think of it as a vector where basically whatever's sitting here and whatever's sitting here, right? If 3 of these plus 2 of these, or no, actually it's just one. What am I doing? If 3 of these plus 1 of these turns out to be 0, I can get to that vector. Okay, this will have a solution. But if 3 of these plus this, whatever's sitting here, is not 0, you can't get there, right? So think of like span is you're talking about input vectors here, you are trying to get to over here, right? So all of these vectors here, the ones where 3b1 plus b2 is not 0, I can't get to those, but I can get to these. This would be the span, right? So the span is that group of vectors I can indeed get to, right? So it might be worth just showing you just what I mean by that. So like, if I were to write 1, -2, -3, 6, but let's say I augment this with, just some random vector. Now there's infinitely many of them that work, right? But let me just pick one that satisfies that. So I don't know. Let's say I were to pick, so I want 3 of these plus this to be 0. So let's say we did 1 and -3, right? So what I'm saying here is 3 of these. I don't know. Hold on. Let me change that lighting. Okay. So 3 of the first ones plus this one would indeed be 0, right? So the point there is if I row reduce that, sure enough, I can get there, okay? Because you're going to get infinitely many, okay, solutions. So the ones I can get to, that way. But let me just change this then. If I were to pick, say, 1 and say 2, right? So now here, 3 of these plus this, that is not 0. Can't get there. That's what the point is, right? So that the vectors I can get to have to satisfy that property. But the point ultimately is, since B is not invertible, does it always have a solution? No, it only sometimes does, right? Okay. But then the same thing, what does that mean? Do they span? No, it does not, right? That's what we were just talking about. So is it onto? No, same thing. It doesn't span. Would it be 1-to-1? Would there be only a one way to get there? No, because there's infinitely many ways to get there. So the one, I changed it, but what did I say? Come on, 1, and then -3. Right on. So those I can get to, but those I can get to in infinitely many ways because there's a free variable, right? Okay. So that's why it's not 1-to-1, because the ones I can get to, is there only one way to get there? No, there would be infinitely many ways to get there, right? Okay. That's pretty much the heart of it there. So you can see how that kind of all relates. But some other points to make here. Let me check out this example 3 here. I'm not going to go through all of these things because it doesn't make any sense anyway. Oh, I forgot to change the letter, but who cares? We'll call this one B2. 1, 2, 1, 4, 6, 5. All right. Now, first off, this example here, this is not square. Okay. This is not a square matrix. So then what does that mean? None of this even applies anyway. Okay. So none of this makes any sense. But I think it's worth talking about this just so you can especially see something like this. Okay. So what I'm saying here is it possible to take this B and multiply by something and get to the identity, even though it's not square? Okay. Well, that's something you probably should be able to figure out, but let me show you the punchline. One thing you should definitely be able to do is, okay, if this matrix B is here, you'd have to first of all think about how big would this be and how big would the identity have to be? Well, this matrix here, remember what we're starting with, this is a 2 by 3. Okay. So in order for matrix multiplication to even make sense, this would have to be a 3 here, right? So there would have to be 3 going down so that all the entries line up. And then the result would be what here and here. But the identity needs to be a square matrix. So this is 2. This would also have to be 2. That way your identity is the 2 by 2, meaning 1, 0, 0, 1. Right? So for time's sake, I'm not going to do it. But imagine what you could do is you could call this, like A1, A2, A3, A4, A5, A6. Set up a system of equations, 6 of them, to figure out what these numbers need to be to make it work. If you go through that process, you will see it turns out to be the next example, right? But you could do it, hopefully. So let me look at these together. The point here is if I take this other matrix example 4 here, right? This one, and multiply these together, right? You can check it out later. Let me just write it here. 1, 2, 1, 4, 6, 5. And then we multiply by negative 11, 4, 4, negative 5, 1, 3. Right? You could, well, whatever. We're already here. We can maybe do it by hand, right? You see that? You're going to get, maybe we'll write it. You're going to get negative 11 here, 8 here, and then you're going to get 4 here. Right? Add these together. 12 minus 11, 1. Multiply these. You're going to get 1 times negative 5, negative 5. 2 times 1, 2. 1 times 3, 3. So you're going to get 3, well, negative 3 plus 3, 0. Then here you're going to get negative 44, 24, and 20, right? 44 minus 44, 0. Then here, negative 20, 6, 15, right? 21 minus 20, 1. Sure enough, you can get to the identity, okay? Now, here's the thing. And everyone said, well, wait a minute. Doesn't that throw a huge monkey wrench in this thing? So is it possible to take a matrix and multiply by A and get to the identity here? Yes, it is. So if this is true, shouldn't all the rest of these be true? No way. Okay, remember, this only applies if A is a square matrix. Okay, these are not square. So, and that's why they're really stressing this idea of on the left or on the right here. Okay. So is it possible to take this matrix and multiply by something and get to the identity? Yes, but that doesn't imply that it is invertible because it's not square. Okay. And then the same thing would be true in going the other way. It's also worth, I'm not going to write it all, but you could check it out. But other things that hopefully you probably want to be able to see how this works. I mean, I know everything is automatically false. Okay. It's because it doesn't work. It's not invertible. But one thing to notice here is okay, so I'm going to put this in here. If you happen to row reduce this, do you get the identity matrix? Well, clearly not, right? Of course, you're not going to get the identity matrix when you row reduce, right? Because it's not square. So it's clearly not going to do that, okay? But one of the things I do want to mention with that is this goes into that whole underdetermined, overdetermined system, right? If you don't have a square matrix, you're talking about either an underdetermined or an overdetermined system. You're never going to get a unique solution. You're never going to get only the trivial solution. You're never going to span all of Rn, right? Whatever the situation is, okay? Because it's never going to be invertible. It's never going to be able to have all pivot columns, right? All that saying the same thing. But even better, again, I think the easiest way to look at that is this one right here. 9 is probably your best friend, right? Because that one you can just look at sometimes. None of the columns are linear combinations. If you stare at that and think about this for a minute, okay? You've got 3 vectors of size 2. You are guaranteed one of them has to be a linear combination of the other 2. Maybe 2 of them are, right? So it's possible, well, okay, so first off, look at these 2. Are these scalar multiples of each other? No, right? That's why they are both pivot columns, right? Now, is this one a linear combination of the other 2? It is, right? It literally says it right there. Look, that third column is 2 of these and negative half of these, right? That's literally another way you could read this. You could read it backwards, right? You can read this as basically that third column, B3, oh no, B3, is literally 2 of B1, what was it, minus a half of B2, right? Check that out. So if I were to take two of these, minus a half of these, that's 1. Oh, that's 1. If I were to take two of these, 8, and get rid of half of that, 3. Oh, that's 5. You see that? So this one literally here is already a linear combination of those two. That's why it happens to be the non-pivot, right? So, I mean, I don't know if this is automatically there, but hopefully then you could see that you have a non-pivot. You're going to get, not only the trivial solution, right? You're going to get basically, can you get to every one of these? No, right? If the ones you can get to, you get to in a bunch of ways, right? Is it going to span all of our right? No, all that's going to be false, right? Also, geometrically speaking, think about that. If you have vectors of size 2, these two are not scalar multiples of each other, right? Meaning 1, 4, right? 2, 6, right? Since they're not pointing at each other, that means these two here, what could you do with these two? I could find some linear combination to get to anything I wanted. Primarily 1, 5 if you wanted to. You could get there, right? But since these two are not scalar multiples of each other to begin with, these two already span all of R2, right? So adding some other third one is not going to add any new information. It's guaranteed to be a linear combination of those two, right? All right. Nothing new here, but let me just let's look at a bigger one just so we can see some of the different examples. So example 5, right? 1, -2, 5, -1, 0, -3, 3, 4, 6. All right. It turns out you can find the determinant of larger matrices, right? And then you can use that determinant to determine if it's invertible or not. We have not talked about that yet. That's later. That's chapter 3, right? So we'll see that in very soon. We'll actually figure out how to find the determinant of larger matrices. It's a huge pain. I'm not gonna lie. It's really annoying. Okay, and it's kind of weird. This is also leading. Invertible matrix is good, right? But it's so annoying to find. Okay. But anyway, you're more than welcome. You can use the calculator on this, or you could just jump right to the inverse. Remember doing that? We talked about that. So if I take C and row reduce it, and the whole point here is if this is invertible, then this part will row reduce to the I, and whatever's left here is the inverse. So the whole point is if C row reduces the identity, then at the same time it will transform I into C inverse. Okay, that's how you can check to see if it's invertible or not. Okay, or let's just use a calculator just to make the point. All right, so let me check, make sure. 1, -1, 3, -2, 0, 4, 5, -3, 6. Okay. Oh, it's worth mentioning here, but if you were to go to the math, see the determinant of A. Oh, look, it's not 0. The negative means something, but who cares? It's not 0. Since it's not 0, what does that mean? The inverse is going to exist. Okay. So you can use the calculator. Sure enough, there it is. Okay. So in this case, your C inverse, let me just write it down, is -6, -16, -3, 1.5, 4.5, 1, 2, 5, 1. Okay, there's your inverse. All right, so that inverse, if you were to multiply it on the left, it's going to give you the identity. If you multiply it on the right, it's going to give you the identity. I'm not going to writing them all, right? But hopefully you see the point here. Does your original matrix, I called it C, whatever. But is it row equivalent to the identity? Yes, it has to be. That was the whole point, right? This row reduced to here, and that at the same time transformed the identity into the inverse. So that is clearly true. Are they all going to be pivot columns? Yes, right? If C row reduces the identity, they all have to be pivot columns. If they're all pivot columns, then that means if you augment it with the 0, you're going to get only the trivial. Or you could use the inverse. Okay. Do the columns form a linear independence? Yes. Yes, right? Because none of them are scalar multiples of each other, right? You can't take some combination of this one and get to here. They are all independent of each other, right? So then the same thing. The equation will always have a solution. The columns will indeed span because I can get to anything. The transformation will be onto all of Rn. Same thing as span, all of Rn. And I can get to everyone in a unique way, hence 1 to 1, right? That's the point. All right. Last one, at least to be able to see it. Oh, I call this D, but who cares? Whatever. I'm lazy. Let's call this C. Okay. Um, okay. Hopefully you're gonna see where this is gonna go and why we did another one here. But let's check this out. Okay. So -5, 2, -16, 7, 3, 5, 6, -4, 24. Right on. One thing you could do is again, let me check out the determinant of that. Uh-oh, the determinant is 0. What's it doing to calculate the determinant? Who cares, right? But we'll talk about that later. But the point is the determinant of this matrix turns out to be 0. What does that mean? The inverse does not exist, right? Or you can literally try to call up that matrix and call the inverse. Look, it is a singular matrix. It can't do it, okay? So this E here is singular. So what that means is if you were to take E and augment it with the identity and you tried to row reduce to the identity and tried to get to E inverse, right? The point is this fail, I should put an arrow in, right? Taking this, the original matrix and trying to row reduce it, you can't get to the identity, right? You can check it out here. If you tried to row reduce that matrix, see, look, you get a row of zeros, okay? You can do it by hand, but the whole point is if you took E and tried to row reduce it, you would get 1, 0, 2, 0, 1, -3, 0, 0, 0, right? So it doesn't row reduce to the identity, which means I can't get the identity to row reduce the inverse, so it does not exist, okay? All right, so now, oh, I should mention, it is a square matrix, so what that means is all of these do apply. The inverse doesn't exist, so the transpose won't be invertible. I can't multiply either way to get the identity. It's not going to row reduce the identity. They're not all pivots. Are you going to get only the trivial? No. Look, I mean, if I augmented it with the 0, look, you're going to have a pivot, non-pivot. You're going to have a free variable, so you're going to have a dependent system here. There's going to be non-trivial solutions. Do the columns of A form a linearly independent set? These two, again, put these together. No, there's a dependency here. Oh, look, you can actually clearly see it right here. What this is saying is that third column, E3, is literally telling me that if I were to take 2 of E1 and subtract 3 of E2, there's your dependency, right? There's your dependency. You can read that from here. But if you check this out, like 2 of these would be -10, minus 3 of these is -6, -16. 14 minus 9. I lost what I was doing. 14, yeah, 14 minus 9 is 5. Right on. 12 plus 12, 12, 24. You see that? I mean, it's literally 2 of these minus 3 of these does indeed give you that third one. But there's your dependency, okay? And that's the whole point, is that they do form a linear, one is a linear combination. So they do form a dependent set, right? They don't stand alone. One of them is depending on the other two. So would the columns of A span all of Rn? No. Basically, they're only going to span whatever these two can get to, right? Since this third one is a linear combination of these two, whatever these two by themselves can get to, this third one is not adding any new information, right? So they're only, all 3 of these can only combine to make whatever these two can make. Well, I should be pointing at these two, right? Now this third one is only already inside of this one, right? So kind of think of it as like, there's this vector here. If I multiply by a scalar, that's going to give me a bunch of other vectors. If I toss this other vector in, now I can get to more vectors, right? Like I probably shouldn't be doing this one from here. Remember, these were independent. So this scalar multiple of this, I can get to other vectors. Combine these two, I can get to more vectors now. Combine these together. Now, since this one is independent of these, putting all 3 of these together, now I can get to all of the vectors in R3, right? Here, scalar multiples. Put these two together, I can get to some of them. But this one on there, but it's adding no new information because this is already a linear combination of these two. That's why I can't get to all of them, right? But then since you can't span, it's clearly not onto this thing here. Would you always have a unique solution? No, you would not. Hence, it's not one-to-one, right? So, I mean, just like I said, this section here, there isn't a whole lot new here. There's nothing new here, but it's kind of cool how it all ties it all together, right?